that an infinitesimal rotation could be represented as a cross product between the original position vector and some differential vector, which would be classified by some direction and an infinitesimal magnitude. So we should be able to write now, there's a pretty neat way to actually visualize this to see how it actually corresponds to an infinitesimal rotation. So imagine we have a coordinate system here, x, y, z, for instance. And let's take, without loss of generality, the n unit vector to coincide with the z-axis. So we then see that if our original position vector r is located here, then n d phi, where phi is this angle here, crossed with this r, gives us this dr vector. And so dr vector will now be the difference between r prime, the new position, to the particle or object here, and its original position. So what this equation actually expresses is that we're dealing with a rotation around an axis n with an angle d phi. And keep in mind from our discussion, I think in the previous lecture, yesterday I mean, that there are two ways to consider this or to view this problem. There's an active way and there's a passive way. The active way is that you leave the coordinate system as it is. You only deal with one coordinate system. And that this rotation then takes us from our vector r in this system to a vector r prime. So we're just dealing with one coordinate system. That's the active way. The passive way is to consider a fixed r vector and then rotating the actual coordinate system so that we get a new r prime vector. And the difference between this active and passive way of considering the problem is that you need a sign change. You need opposite direction to have the same equation. So what we've done here is the active consideration. So one application of this consideration of infinitesimal rotations is that it allows us to say something about the time change of vectors and how the time change of a vector is perceived differently depending on which coordinate system you are positioned in. So the point is that for an arbitrary vector, the evolution of this vector in time, or how it changes with time, will depend on what kind of coordinate system you are positioned in as an observer. In particular, whether or not this coordinate system is rotating. So this arbitrary vector g can be both position, velocity, angular momentum. So the rate of change with time of an arbitrary vector g will in general be perceived as being different in the coordinate system attached to the body center of mass, for instance, as compared to a stationary or external coordinate system. And the difference is due to the possible rotation of the body's coordinate system as seen in the external or fixed coordinate system. So one way to see this clearly is to consider a vector which in the body's coordinate system is fixed. So to illustrate this, let's just consider a simple example of a body which is rotating around the z-axis. Let's say we have some vector here, g. And so we're considering the scenario where this vector g is fixed in the rotating system, which means that an observer in this stationary xyz system would see g as rotating, whereas an observer in the rotating coordinate system would see a constant vector. So we can express this mathematically by saying that the infinitesimal change of g as seen in the body coordinate system is 0. So then one might ask, what is the rate of change for the vector g as seen in the fixed coordinate system? Well, we know the answer to this actually, because the scenario considered here is equivalent to the picture here. the infinitesimal change in a vector is given like this. So a vector which is rotating with a body's coordinate system will be seen as changing in the space system as follows, where omega here represents both the axis of rotation and the angle the vector has been rotated, namely d phi in this case. So the general relation between how a vector is changed in the body compared to the space system is given like this. The change in the space system, the fixed system, is given as the change as seen in the body system, plus this extra term, which stems solely from the rotation of the body system compared to the space system. And so we see that we're now in a position to actually be able to say something about the rate of change of a vector with time. Let me just divide on dt. So we see that the rate of change from an arbitrary vector g in the space system is given as the rate of change as seen by an observer in the body system, plus the angular velocity, or the rate of rotation of the body crossed with g. So omega here is the angular velocity. Now we haven't specified g, we've just said that it's an arbitrary vector, which means that we can essentially view the framed equation over there as an operator relation. Like this. So we consider the time derivative operator, as seen from the space system, should be equal to the time derivative operator in the body system plus omega cross, and then insert vector. Yeah.
Did you neglect that term dg dt in the cross product in the y?
No, I don't think so. So I just took this dt here. If I had dt squared, then I should have g dt here.
No, but could you have taken g divided by dt in the cross product also?
I'm not sure I see exactly how I mean. So we agree on this one, right? Okay, so then I just divide on dt. So I get dg dt here, and I get dg dt here. And then for this term, I just divide this one on dt.
But why just that one? Why don't the entire cross product?
Well, we have, in general, we have a cross product and divide on a scalar. I can write this as A over C cross B, or A cross B over C. It's just one factor.
So it's just a scalar, right?
Yeah, dt is just a scalar.
Okay.
So it's just one factor. I can bring it here or I can bring it here. So it makes most sense to bring it here, because then we can express this as omega. So one specific and important example of how we may use this operator relation is to consider the position vector. In which case this operator relation provides us with the following equation. And we can see that this makes sense, because if the velocity of some object in the rotating frame of reference is 0, in effect it's some vector attached to the reference system which is fixed, then this is 0, and the velocity as seen from the fixed coordinate system is just this angular velocity crossed with r, which gives us the linear tangential velocity for a circle, for instance. So there's an extra term here always when the frame of reference of the body is rotating compared to the fixed frame. There's one other way to see why this has to be the case, which is quite instructive, so I'd just like to show it to you here. And let's just consider 2 dimensions for simplicity. If we have some vector g, it can be written as an x component multiplied with x unit vector plus the y component and the y unit vector. Now, if I have a vector in some coordinate system, I can always represent that vector by another vector in a different coordinate system. Like this. So a vector in this fixed coordinate system I can always express as a vector in the rotating coordinate system. But here comes the essential point, and that is how to deal with the time derivative of this vector. Well, if we were an observer in the fixed coordinate system, we would just write this: the rate of change of the components multiplied with the unit vectors. However, when we derive this equation here, as seen in the fixed stationary system, should be a prime here, by the way, I get this, but now I get an extra term. Namely, the derivative of the unit vectors. And these are non-zero precisely because the system is rotating. So whereas we can always write a vector both in the fixed and the rotating system, we have to be careful about the derivation because these unit vectors now are time dependent. So this sort of gives us an explanation of why we obtain this extra term here. Because you can show mathematically that if you have a rotation of this body system, then these unit vectors can be expressed like this. Okay, so we said that the rotation of the body system was characterized by some angular velocity omega. Now, using our framework that we have introduced of how to deal with general rotations, let's say we're interested in expressing this omega vector in the rotating system. Now, there's an important conceptual pitfall related to this. Because if you're an observer positioned in the rotating system, what kind of angular velocity do you see? Zero, right? So then one could say, well, what's the meaning of this? How can we express omega in the rotating system? It should be zero. Well, there's a difference between what kind of angular velocity an observer in the system would see and mathematically expressing a vector in the original system in terms of the unit vectors in the new system. Right? So what we're doing is just that we're taking this vector, which is defined in the new, old coordinate system, and then expressing it in the new coordinate system. It still has a value there. Even though an observer will not see any angular velocity. So we're just considering this as a mathematical quantity. Since we have seen that a general rotation in 3D may be expressed through these three Euler angles, phi, theta, and psi, then the angular velocity of a rotating object should be possible to express by means of three successive rotations that have angular velocities phi dot, theta dot, and psi dot. This should correspond to an arbitrary angular velocity vector. And if this is the case, well, then we're in a good position because we know how to go from the original coordinate system to the new one by means of these transformation matrices B, C, and D. So let's consider first the angular velocity due to the time change of phi. And that corresponds to the first step, where we had a matrix D, I think. So the first angle phi corresponds to rotation around the z-axis, which means that the angular velocity thus points along the z-axis because the angular velocity points along the axis of rotation, and it has a magnitude phi dot, the time derivative of phi. And the objective is to find the angular velocity in the final rotating system, the XYZ prime system, if you will. So we know how to do this. We just have to multiply this vector in the original system with the A matrix, which was equal to BCD, the total transformation going from the original to the final system. So we have this relation. Okay, next we would have an angular velocity due to the rotation theta, which was the next step. Now theta corresponded to a rotation around the xi prime axis, if you consider your notes. So expressed in that coordinate system, which should be xi prime, eta prime, zeta prime, this angular velocity can be written like this. Its direction is along the axis of rotation, which is the xi prime axis, and its magnitude is theta dot. So it's important to be aware of the fact that these two vectors have now been written in different coordinate system. This is the XYZ coordinate system. This is the xi prime, eta prime, zeta prime system. And if that is the case, we know that there's just one transformation separating our present coordinate system from the last system which we desire to obtain. Meaning that we just have to act on this vector with a B matrix. And finally, the angle psi corresponds to rotation around the zeta prime axis, which is equal to the z prime axis. So the angular velocity due to the rotation of psi has a direction which is equal to the axis of rotation, the z prime axis, and its magnitude is just psi dot. Now, in this case, there's no transformation needed because we're already in our final coordinate system, because we're dealing with a rotation around the z prime axis. And so we now have all of the components. We have expressed the vector, the angular velocity corresponding to the rotation with phi in the final system, and the same thing for theta and psi. So to complete So the complete set of transformations looks like this. This will be the angular velocity vector in the rotating system expressed through these Euler angles that describes the rotation. You see that in general you will have a contribution from all of them. Very well. Now, in the context of rotating coordinate systems, there is a force which you might have heard of, which is known as the Coriolis force, which is something that appears precisely due to rotational motion and the different perspective as seen from a stationary system. So the way we'll do this is to use our operator relation. Like this. So we can use some kind of example here. So basically imagine that you have some fixed coordinate system here in the middle, and you have a rotating coordinate system here. Which is characterized by some angular velocity omega. Now, in deriving this relation, we actually assume that the origo of these two coordinate systems coincided. Right? We had a fixed system, and then we had a superimposed rotating system with the same origo, with the only difference being that it was rotating. Now I have a slightly different scenario. I have a rotating system with an origo that does not coincide with the stationary system. So if I have some vector here, I'll call this R. So let me denote R as the vector to this point as seen from the stationary system, and large R as the vector connecting the two origos. I should have this. So the position vector as seen from the stationary system is given as the position vector as seen from the body system plus the vector connecting these two origos. So you see that in that case, there's actually a difference from this operator relation. Namely, due to the fact that you could in principle have a movement of these two coordinate systems relative to each other. This term, the time derivative of our body, gives these two terms, as we've seen before. Since these unit vectors describing the direction of the axis in the new coordinate system rotate. But we have an additional term here. So we have to be careful about what these terms actually represent, depending on what scenario we have. So in scenario 1, where the two coordinate systems coincide with their origo, we saw that we had this equation. So what this means is then that the velocity of this radial vector, or the velocity of this object which is situated in a position r, as seen in the fixed system, is equal to the velocity of the same object as seen from the body system plus this extra term due to the rotation. Okay, that's the first case. And consider now the second case, which we have illustrated here, in which we have still a rotating system, but now the origo is different from this one. So there's a vector connecting the origos. If we make the assumption that this vector is a constant, which means that its time derivative is equal to 0, and then again consider some object situated somewhere in space, which has the position vector r as seen from this fixed system. then we have to be careful about what the terms in this equation actually represent. Because we still have the same operator relation, but now Vs, as before, is the velocity of the object as seen from the fixed system. Vb is the velocity of the object as seen from the rotating system. But then one can ask, okay, so which r should we use? The answer is that it's the r, it's a position vector as seen from the body system. And this becomes clear from this picture here, that the r, small r, as seen from the fixed system, is equal to the vector connecting the origos plus r body here. In this case, the r is unambiguous. There's just one position vector to deal with. Now, we can write it differently in the two coordinate systems, but there's still just one vector. In this case, we have to keep in mind that this operator relation means RB as seen from the body system. So I just wanted to underline this distinction, because we might not always be as lucky to have a situation where the two coordinate systems coincide. For instance, if we want to deal with Earth orbiting the sun, then we would have something like this. Are you, yeah?
It says previous lecture that you can move the dt to the second term in the cross product. What if you do it to this formula here and get the dt to the rb vector? Then the r dt vector is equal to the dr dt vector.
I see what you mean, but we don't have dr, we only have r. So keep in mind here that we had... so let's say g is r, so we had this equation. And then we divide it on dt. So if we move dt to r, we have d omega cross r dt, which doesn't make much sense. So the only way to actually describe this as a new vector, omega, is to move this here. Yeah. Okay, so let me just outline then the derivation of how the Coriolis force appears. So we have this relation, and then keep in mind how to interpret these terms depending on what situation we have. Now insert this Vs into our operator relation, which should be possible because it's valid for an arbitrary vector. And I'll guess that's how far we get. We'll continue next time.